Video 2, IP Subnetting, ARP, and Ping. This video describes the task number 2 of the V-Day 1 book, Introduction to Enterprise Routing Practice, that you can download in PDF format at www.juniper.net/day1. Let's start with the basics. The multi-access network connecting H, R1, and R2 in our practice has a network address of 10.1.1/24. In fact, 10.1.1 is the short form of 10.1.1.0. This network address is not assigned to any host or router interface. So what does /24 mean? It's the network mask. Let's see how it works. Here is the network address in binary format. It has 24 significant bits, and the remaining bits are set to 0 in order to make up the network address. We can build host IP addresses by playing with the 8 remaining bits. The all 0 and all 1 values are reserved, so we are left with 254 possible values. The first host address is 10.1.1.1, and the last host address is 10.1.1.254. The all ones address is the broadcast one. It represents all the hosts in the subnetwork. So if you ping 10.1.255, all the hosts in the subnetwork will reply. Let's now see the example of the link between routers IX1 and I. It has a /30 mask, very commonly used in point-to-point links. The 2 bits in blue are the ones that we can play to make up host addresses. The first host is 172.16.1.1, and the last host is 172.16.1.2. So /30 only supports 2 hosts. That's why it's only used in point-to-point links. And finally, the broadcast address. Let's see a slightly more difficult example. In this case, the last octet of the network address is 52 and not 0 as it was in the previous examples. The mechanics are the same though. Think binary and you'll understand it easily. Now let's see an example of a loopback address. This one has /32 mask, or, in other words, one possible address that is assigned to the local host. Indeed, loopback interfaces are never connected to any remote device. So what's the magic behind a ping operation? In Ethernet networks, more than 2 hosts can be connected to the same multi-access media with their own Ethernet interfaces. Each of these Ethernet interfaces has a physical or MAC address. In this diagram, we have H, R1, and R2 connected to the same virtual bridge or level 2 switch that belongs to the Juniper infrastructure. When H tries to ping R1, it first needs to know the MAC address of R1's Ethernet interface. That's the purpose of the Address Resolution Protocol, widely known as ARP. The ARP request is a broadcast frame that is flooded to all the hosts in the Ethernet domain. The ARP request is sourced from the unicast MAC address of H, that we call here PHI or PHI. Since the source MAC address of the ARP request is PHI, the level 2 switch maps PHI to the port connected to H. This process is called MAC learning. Since the ARP request is asking about 10.1.1.1, R1 answers with an ARP reply. This ARP reply is targeted to MAC PHY. So the level 2 switch is clever enough to forward it only to the port connected to H. And it performs MAC learning for alpha, the unicast MAC address of R1. When you ping from H to R1, an ICMP echo request packet is encapsulated in a frame whose destination MAC address is alpha. So the level 2 switch only forwards it to R1. And a similar principle applies to the ICMP echo reply, and that's ping in action. Let's see the ARP process in detail. The ARP request has a unicast source MAC address that we call PHY. Every MAC address has 6 octets. The ARP request is targeted to the all ones MAC address, also known as the broadcast MAC address. On the other hand, ARP replies are targeted to the unicast MAC address of the requester, in this case, PHY. Finally, when you ping from H to R1, the ICMP packets have unicast destination MAC addresses. And since the level 2 switch has already learned these MAC addresses, the packets are only flooded to the relevant ports.